Hello, should finally hear me. I got Zoom kind of made me log in 2 or 3 times. I got mixed up with Zoom. Okay, so you should see me or hear. You should see the desktop and hear me by now. Does that seem okay?
Yep.
Okay,
Yes, sir.
thanks. Okay, let me. Okay, okay. Let me think. There. Oh, there's a homework assignment due today, and there'll be another one up there by soon. Okay. If you have questions about the homework assignment, send me emails or come to office hours. Okay. And today we're going to finish language 7. And I'm not sure if we'll have time to start language 8 or not. I haven't put it up there. I have it on my computer, but I'll put it up there too. Language 8 is a big jump to go from language 7 to language 8. So where we were in language 7 was looking at how you evaluate function calls. And what we want to talk about a little bit is the difference between dynamic scope and lexical scope. It's historically kind of interesting to look at. I mean, very few languages these days would do dynamic scope. I think there might still be some languages out there that do dynamic scope. It's considered a mistake, but there's the idea between dynamic and lexical scope comes up every once in a while in computer science theory, and every once in a while people propose it as an idea for a language. So let's look at what I mean by that. So we want to talk about lexical scope. What is lexical scope? And the alternative to lexical scope, what's called dynamic scope. Okay. See, and lexical scope is also sometimes called static scope. So it's not as often static scope. Should be a synonym for I think it's of static scope is just a synonym for lexical scope. Okay, so let's look at some. Okay, let me unzip language 7, and then I'll write a little bit of code to give an example of the difference. Okay, I don't remember if we wrote an example last week that describes the difference. Let me see. I can't remember if one of these. No, those didn't. It wasn't there. I thought we did. I thought we mentioned. Okay, let's write an example where. Yeah, I don't think I mentioned it briefly, and I don't think if I wrote an example, I didn't save it. Okay, so let me create a file. Okay, dynamic. Okay, lexical versus dynamic dot language 7. So we'll create an example in language 7. Okay, that's lexical scope versus dynamic scope. Okay, and lexical versus, that makes it easier to read, lexical versus dynamic. So let's write a little example. Okay, so we're going to write a program. Okay, I'm going to create a variable there, x equals, say, 1. Okay, and then I'll define a function, fun f lambda y, and this lambda function will take, this function is going to just add its parameter to the global variable. Okay, so we've got a global variable here, and add parameter to global variable. Well, we'll see that that's actually lexical. Actually, let me just say what I'm going to add to, because the whole point is x is not local to this function. So what I really should say here is that x is a non-local reference. That's the phrase we use for it, a non-local reference. Now, if I gave this function another parameter, now x is a local reference. Now x is that parameter variable. Okay, if I do this, now I've got another another local. See, now that would be local variable, global variable, well, non-local variable, local variable. Okay, so the local variables are the ones that are declared in the function. That's what we mean by local variables for functions, the ones that are declared in the function. If you make a reference to a variable that's not one of the parameters, it's called a non-local reference. And then the question is, where do you get it from? Okay, where should it come from? And the choices are going to be dynamically scoped or dynamically scoped or lexically scoped. Okay, now I'll create a begin block. Okay. Okay, and in the begin block, I'll declare another variable, x, that's a local variable. Okay, so this is a local variable. It's local in this. It's local in this block. Okay, call the function f. Apply f to say 5. Okay, and I'll store the result in a variable. Also, I'll create another to see the result. I'll say var result. Apply f to 5. Okay, and close the begin block and close the program. Okay, that should be a little program. And the question is, which x should f use? Okay, now when you call f, you go up to here to here. Here's f. Oh, I don't need that z anymore. You get up here. Okay, that x could be that one because that's what's in scope lexically. Remember, that was the idea that if you go back and see what's the last place you declared an x, it's there. But the other hand, you might ask, when you call this function, what was the last x that was created? The last x that was created was this x. Okay, so then you might say, well, this function should use the last x that was created, the last x that was declared. That would be dynamic scope. Okay, so oops. The way we think about it is use x equal to 1 is lexical scope. And if we use the x equal to 10, that is an example of dynamic scope. Okay. If we use this one, it's lexical because we can see that in the way the program's laid out. At this point, the only x that's been declared is that one. So that's one we should use. We say that x is in scope. Okay. Now, if we don't use lexical scope, we can just say, well, what's the last, when we get to here, we can just say, what's the last x that was created? Now, that's a dynamic thing because, for example, if I come down here, suppose I extend the program by doing another begin block. So I'm going to extend the program. Here's another begin block. And in this begin block, I create another var x 1000. Oh, that equal doesn't belong, I'm mixing up syntaxes there. I'm mixing up, tradition, saying, oh, I did that up here too. I'm mixing up syntaxes. Okay. So var x is 1. Okay. Here I can say var x is 1000. And then I can call f again. Var r apply f to, say, 5 again. Okay. And close this begin block. Okay, and close the program. Okay, again, same thing. What x do I use? If I'm using dynamic scope, I would use this x, because that now is the last x that was declared. Okay, here I used, if I'm using dynamic scope, this would be the last x declared at this point. Okay, now you end that begin block, so this x goes away. Oh, and then suppose I do here, apply f to there are apply f to 5. Okay, so now the program declares this x, declares that function. Then in a begin block, it has a local x, calls the function. In another begin block, it has another local x, and it calls the function. Then it calls the function one last time. Okay, if we're using lexical scope, f is going to be the same here, here, and here. Because when you get here, you just say lexically, that's the x. But if you use dynamic scope, this call to f would use the last x that was created. This call to f would use the last x that was created. And this call to f, well, the last x that was created and it still exists is this one up here. Because this x fails to exist at that point, and this x fails to exist at that point. So now this f would go ahead and use the global one, because that would be the last one declared. That would be the most recent one declared, because it's still there it's still in the global environment. So the other ones have disappeared. This one will have disappeared by the time you get to here. Now notice that dynamic scope makes programs really hard to read. What does this do? Well, you have to figure out what's the last x that was laying around, that was defined. What does this f do? Well, you have to know what's the last x that was created. What does this f do? Well, it's this one, you referred to that x. Okay, and you can make this confusing as heck. You could put a call to f right there. This f uses that x, this f uses the global x, this f uses that x, this f uses the global x. If you use dynamic scoping, this is why it's fallen out of favor. Dynamic scoping can be really hard to track down. Now, let's see. If we use dynamic scoping, let's see what the result would be. If we use dynamic scoping here, we'd add 5 to 10, and we get r equal to, let's see. With dynamic scope, r equal to 15. Okay. And here, with dynamic scope, r equals to, well, 6. Here, with dynamic scope, it would be r is equal to 1005. Okay. And with dynamic scope, this one would give you r equals 6. Now, with static scope, they would all be 6. With static scope, every one of these would return 6. Okay. Now, right now the language is using, okay, let me run this program. I run this program by going over here, calling up a command line. call the interpreter. The interpreter is language7.cmd, and I want to run it on the program Lex versus dynamic. Okay, oops. Oh, okay, I got a syntax error in this program. I'm missing some parentheses is out of balance. Let's see. So close that one. Fun. Oh, right at the beginning there. 1, 2, 3. This one needed a third parentheses. Let's see if I did any other ones. Okay, that was one out of whack. Okay, there's a parentheses. Open, close, open, to close. Okay, this one closes the begin. Okay, 2 here. This is what Lisp programmers do all the time. This is one reason why Lisp is a little bit not, not everybody's in love with languages like Lisp, because you count all these parentheses. I don't know, did I ever show you all the jokes about Lisp parentheses? Oh. You can see it's a joke about floating parentheses. Another one he made was these are your father's parentheses. Yeah. The idea, see that guy, why he's dressed as a wizard? He's the wizard from he's the wizard from this textbook cover with the lambda. This textbook is in, so that's why this guy's kind of dressed as a wizard. He's meant to be this wizard with the, here it's a lambda, here it's parentheses. Because in Lisp, you just type parentheses. You have to get all these parentheses closed. You have to get all these parentheses balanced. And it's not just Lisp, it's Lisp, enclosure. There's a family of languages that use this notation. And it has the problem that it can be really tough to get all your closing parentheses in line. I think let's see. Now go over here and just rerun the program. I think I got it right now. There. Okay. So I was missing only one parentheses. Okay. Now trace through the interpreter. Let's see what the interpreter did. Here's what our program looks like in, the pretty printer takes that and makes it more C-like. So we got a global variable X, a function Y that refers to, well, that's the non-local reference. If it's a C language, that is X. But in a dynamically scoped language, that X doesn't have to be that X. Okay. And then here's a block with a local X, and you call that function. If you use dynamic scope, then that X is that one. Then here's another call to the function. Since there's the only X now is that global one. Now here's a local X. That X is more recent than the global one. So if you do static scope, this function F will use that X. Okay. All right. So right now the interpreter is doing static scoping. So here's the X in the global environment. Okay. Here's the F in the global environment. So we've got two global variables, X and F, the function name. So we've got X and F in the global environment. Now here's a call to F. See, this is the begin environment. So this is creating the local variable X. So there's the local variable X. Okay. Now here's the function activation. The function activation doesn't even use the local environment. See, the activation's chained to the global environment. That's the static scoping. This function is chained to the global environment for all its non-local references. So this function, no matter where you call it from, it's always going to chain itself to the global environment. And we'll see in the code where it does that. This function always chains the activation record to the global environment, never the local environment. And that's what we'll change. If this activation record is chained to that local environment, then you have dynamic scope. See, it's going to be see what this arrow points to. If this arrow points to the global environment, it's becomes static scope. But if that arrow points at this local environment, we'll change one line of code and we'll make that thing point to this guy, and then we'll have dynamic scope. Then we'll pick up that X, not the global X, because then the chain will be activation record to local environment to global environment, and this X will hide that X in the dynamic scoping. So every time we activate the function is activated chain to the global environment. Okay. Again, here's another activation. See, here's another activation. It's chained to the global environment. That's the second function call. And then here's the third activation. And again, yeah, all the activations are chained to the global environment. Okay. So there's one, two, well, there's 4 function calls. So I missed one of them. There's 4 function calls. So we should be able to find 4 function activation records. There's one function activation record tied to the global environment. There's the second one tied to the global environment. There's the third one. Where's the fourth? Let's see. Why am I missing one? Did I count right? There's one. There's one function activation. 1, 2, 3. Oh, the program crashed. Oh, okay. I made it. See, I made a runtime error. Oh, because I declared the variable twice here. This should have been set. See, that declares a local variable. Okay, that declares a local variable in the begin block. This creates a global variable R. This creates a local variable X and a local variable R. Then you can't recreate the global variable R, so I need to set the global variable R, or make this R1 and make this one R2, for example, for I have 2 global variables. But that was, I mean, I had a run. Notice that runtime, that's why you like compilers. Compilers give you syntax errors at compile time. With languages like Python and like this, I mean, this is very much a JavaScript like Python-like program. You don't find out these mistakes until runtime. You know, the fact that I redeclared a variable showed up at runtime. You know, now later on I'll give you a homework assignment and you can fix this problem at parse time. So I'll show you how, you know, you'll have a homework assignment where undeclared variables or redeclared variables are actually kind of easy to find at parse time. So this problem here of me having the same variable declared 2 times, that's actually pretty easy to solve at parse time. So that'll be one of your homework assignments later on. Some of the other runtime checks are much harder to do at compile time. But finding undeclared variables or redeclared variables is actually pretty straightforward. It's not trivial, but it's a good programming exercise. It's a good homework exercise to see how that you can at parse time. We don't have a compile time, but at parse time you can find these variables that were redeclaring. So I can just do this, okay? Then go over here. Now rerun the program. Okay. Notice it didn't crash. See, it didn't terminate with an exception. See, I didn't pay attention that thing terminated with an exception. And now there'll be the 4 function environments. Okay, there's the last one. Okay, now let's go look at the evaluator and look at the code to handle a function call. Remember, this was the code to do a function definition. We did that the other day. Now we're interested in apply. Here's apply. This is the function call. Okay, and you know, it turns out there's 11 steps to this. Okay, real quick, you get the function value. You have to evaluate it. You have to, if you look at the syntax, you apply, well, what you apply is the result of that expression, and it's supposed to give you a lambda. If it doesn't give you a lambda, you get a runtime exception. Now, usually that would be the name of a function that just gets looked up in the environment and it gives you back the lambda it's the name of. But we showed examples the other day. This could be an expression. It could be an if expression, or it could be a function call that it returns a function. So this could be anything that returns a lambda to you. So this needs to be evaluated to a lambda. So the first step is evaluate that first expression, and the second step is make sure it's a lambda. So you get back a value. I called it fun value for function value, but you don't know that it is. So you got to make sure it is a function value. If it isn't, and the way you can get that would be like if you wrote something really dumb, like I'll put it down here at the end. Apply 5 to 4. Okay. If you run this, okay, bad function value. Well, 5 is not a function. You can't apply 5 to 4. Another example would be x is a variable that's an int. Okay. If I apply x to 4, I end with bad function value, x. X evaluates to a number, not to a function. Okay. So I need to apply something that evaluates to a function. In this case, now I could do the following. If true, f, else 0. Okay. That'll work out okay. Well, what did I write wrong in the conditional? Oh, there's no else in our language. If Boolean, if it's true, do this. If it's false, do that. There's no else in the language, just like in Lisp. There's no else in Lisp. Okay. Okay, that evaluated fine. Now, if I change this to false, now it's not going to evaluate fine, because instead of returning this, the if expression is going to return this. See, apply evaluates this if and checks to see what it gets back. Now the if is going to return the 0, and then apply is going to say, I don't know what to do with a 0. Okay. Bad function value. The bad function value is in here. The bad function value is actually the 0. Okay. So I'm not giving the world's greatest error message here. Bad function value in the apply, and it's, you have to figure out that this thing returns 0, which is not a function value. But when you had true there, that was okay. True here caused the if statement to return f, which is fine, because the value of f is a lambda expression. Okay. Right. So in the evaluator, evaluate the expression after apply, make sure it's a lambda. Okay. All right. Okay. So now it's a lambda. So now you, like if we go over here, there's our abstract syntax tree. Okay. When we apply an f, like here's the first, when we apply an f, we look up f and we find out it's lambda. See, I'm applying f. I've got that reference now to that lambda. So I'm applying actually that lambda. So that's what this next line of code does. The next line of code says, well, get me the lambda. Get me the pointer to this. I'm applying f. I find out that f is that lambda because it's, I've declared f to be that lambda. So I want a pointer to that lambda because that's where the function code is. So I get the lambda expression. So the lambda expression stored in the value, okay? The lambda value stores a pointer to the lambda expression, which is a tree. So now my apply is pointed at that tree. Now that's useful because that tree says, here's the parameter, and here I know that's the argument. So I need to create remember, next step is to create an environment that holds a variable y and a value 5. Okay, so apply is pointing at that lambda. Apply needs to bind that argument to that parameter. Okay, so that's next. Create this environment. Okay, now here's the thing that ties the environment to the global environment. So this is the line of code. If we change this to this, it's now lexical scope or dynamic scope. This environment is the one that he was passed when he was called. So that's the current environment. If the activation record is tied to the current environment, that we'll look at the picture. If the activation record is tied to the current environment, that's dynamic scope, because the current environment holds the most recent variables. So then this guy would be chained to the most recent environment that holds the most recent variables, and it would start looking things up in the recent variables. The way it was, this function, it's the function's local environment, which holds the arguments to the function, it's chained to the global environment. So the function looks up the non-local references in the global environment. Okay, so you can't, now that doesn't show up in this picture. You know, at that little step you can't visualize that over here. You have to visualize that when the program's running. But the lambda, notice it's got a non-local reference right there. So there's this issue of where did that x come from? You know, static scope says it comes from here. Okay, but that doesn't show up in this picture. There's nothing in this picture that says that add x should be that one. How come that x isn't that one? So if you look at this picture, well, it's closer to that x. You know, it's farther away from that x. It's closer to that x. So why doesn't it be that x? Well, in fact, that's what dynamic scope would do. Dynamic scope would make that x because it's closer to the supply. This would be the most recent environment. See, the begin would create this environment, and apply would be chained to that environment in dynamic scope. Okay, so if we were using dynamic scope, when we got here, this would be the environment of this begin. That's the most recent environment. This, we're evaluating apply inside this begin. So the current environment is the environment of that begin block. So this guy is that begin block. Okay. If we create an environment for apply using the begin block, that's this line here. If we create the environment for apply using that environment there, then this guy would be looking up variables in the begin block. And the begin block is tied to the global variables. So the begin is tied to the global variables, but apply would be tied to begin. So then F would find that X. Okay. And we'll see it when it runs, we'll see it happen that way. Okay. So there's the difference. One, there's global scope. No, see, there's global scope. I'm sorry. There's lexical scope. There's dynamic scope. Lexical scope, dynamic scope. Back in the 1950s and 60s, when they were inventing this stuff, they didn't actually pay enough attention to what they were doing. They just thought, oh, we should be, they actually admitted it was a bug. When they finally figured out what they did, they said that it wasn't the right thing to do. They just wrote their code saying, well, there's the current environment. So let's, evaluate in the current environment. Yeah. So let's just we chain the new environment to the current environment. The new environment is going to hold the bindings of the arguments. And they just said, well, chain it to the current environment. That turned out to be a mistake. That created dynamic scope, which turned out, as we saw, dynamic scope is hard to read. Dynamic scope makes every one of these function calls do something different. Yeah. Dynamic scope makes these function calls all act funny. But actually, some people fell in love with dynamic scope because you can write some pretty crazy programs that using dynamic scope. People then took this and ran with it and wrote real clever algorithms that depended on the existence of dynamic scope. The algorithms were fast, but also completely opaque. They were hard to understand, hard to write, but they were fast. But some people thought that was clever. So there were people in the world who thought dynamic scope is fun because I can write really clever algorithms this way. And I don't care if anyone can read my algorithms; they work. But it made programs really hard to understand. So the world settled on static scope. So this X is that X. Okay, so that's pretty much every modern language now does it that way, static scope. Okay, so that means that you have down here, you have to you chain the new environment to the global environment. So down here, when you get to the apply, you ignore the begin environment and you chain the apply to the global environment. Okay, that makes all the function calls do the same thing. Okay, now after you create the local environment and you can bind it to whoever you want, then in the local environment, in this environment, you start binding arguments to parameters. Actually, this is the parameter. This function's got one parameter. This function call's got one argument. Okay, so I'm going to create an environment that holds y equal 5. Okay, so I do that in this code here. It's a for loop because there might be more than one argument. So a function could have 27 parameters. So you have to loop through all the arguments in the apply. The left branch is the function. Then there's all these other right branches that are the arguments. There could be lots of them. So you loop through all the argument values. For each argument value, you have to, this could be a formula down here. So you have to evaluate the function argument. Okay, it doesn't have to be a constant like 5. So you evaluate the function argument. Now you evaluate it in the begin environment. See, this stuff here should be evaluated in the begin environment. So if I go back to my example over here, if I put X here, that X should be this X. But the function's F, see, so notice that here, that X should be this one. But when I get inside the function, the question is, what should that X be? Okay, so it doesn't matter if I use dynamic or static scope. If I do this, this guy should be that. Okay, so over in this picture, when you're binding this variable to that parameter, when you're binding this value to that parameter, you have to evaluate this formula first. Like here, I just made it simple. It's just a constant. But you have to evaluate this in this environment. Okay, so you have to evaluate the actual parameters in the current environment, the environment this function was called with. I say, this stuff is a little bit tricky. This is the kind of programming, when you get past simple little, JavaScript making, web pages, and you get to, more sophisticated algorithms and data structures, this is the kind of programming you get. You have to really think hard, keeping track of what's going on. You have to think about what I'm doing in my code, what I want my code to do. I'm evaluating arguments. They have to be bound to parameters. I have to evaluate the arguments in a certain environment while I bind them in another environment. So I'm evaluating the arguments in one environment, and then I'm binding them into the, where is it? I'm going to add them. I'm going to bind them in this environment I'm building. So this is the environment I'm building. Okay. While I'm building it, I'm using the current environment. Okay, so for each argument, I evaluate the argument, reach over into this lambda expression and get the name of the parameter. So I reach over into the lambda expression. This evaluates the argument. This reaches over into the lambda expression and gets the name of the parameter. This checks that it's really a legitimate variable name. I mean, somebody could write a kind of a dumb piece of code. I could go back over here and I could write that. I won't find out that that's a mistake until I try to call the function. And then at some point when I call the function, I'll run this. It isn't until I call the function for the first time that the interpreter goes over here and says, wait a minute, that's not even a valid variable name. Again, that can be fixed. That's one of the ones you'll fix in your code. That's one of the ones that can be fixed at parse time relatively easily. But right now, the interpreter doesn't even know that that's a mistake until it tries to call that function. So if I go over here to now over here, if I run this, okay, improper parameter name 5. See, it was when I tried to call the function that the interpreter at runtime, when it tried to, when the first time it tried to call the function, it got up here, that code came from this line right here. It got the formal parameter name, checked that it matches a parameter name, and it found out, nope, improper parameter name. Yeah, that's a bad time to find that out. That's again, that's there's interpreted languages like Python and Ruby and JavaScript, they tend to have these kinds of problems. You don't find out about mistakes until runtime. And then there are tools that try to solve this problem for you, and you'll write one of those tools for this language. You'll write something that tries to find as many of these errors as possible before running the program. But it's the nature of the language that you can't find all the mistakes. You can only find some of them before running the program. You need a full-blown compiler to be able to find all the mistakes before running the program. Okay. All right. So we find out, okay, if we go back to this one, let me go fix it. Yeah. So that was an example of an improper parameter name. Okay. Oh, there's other mistakes are like repeating a parameter name twice. That would be a mistake. You know, another, that would be in our case a runtime error, though it should be a parse time error. So an improper parameter name, repeating a parameter name twice is illegal. Now, having a variable it isn't a parameter is not a problem. It's just a non-local reference. Okay, so if I put a z there, there's nothing wrong with that function. It's got a parameter y and it makes two non-local references. Now at runtime, there'll be an error that there's no z anywhere in the program. Okay, but there is an x up here, so that's okay. Okay, so there's something like this error would be very hard to find without running the program. That's an example of an error that we would not be able to probably figure out. Well, that one, if it's lexically scoped, we can solve that problem, because lexically you can just go back up here and say there's no global z. So it's with dynamic scope, you wouldn't be able to tell, because there may or may not be a z declared somewhere else in the program. So if you use dynamic scope, there's no way you can figure out that that's wrong until you actually run the program. If you do lexical scope, yes, you can find out that there is no z in this program. So that will be one of the ones you will be able to catch. With lexical scope, you'll see that z, no, there isn't a z anywhere. Okay. Now the fact that there might be a z down here, that would mean that this would be okay dynamically scoped, because it'll get that z down there. But that won't matter for lexical scoping. Lexical scoping just says, I only go that far. I only look for z's there. Before that, I only look for global z's. So lexical scoping makes things easier to solve. Dynamic scoping, that's another problem with it. It makes it really hard for even a compiler. Even compilers can't tell if this is legitimate or not until you run the program, because there could be z's all over the program and you have a hard time knowing whether one of them is in existence or not when this function is called. The error would be if this function's called without there being any z in existence. but that's a tremendously hard problem to solve. Not even compilers can do that. That's another reason why lexical scoping took over dynamic scoping. Compilers can't even do dynamic scoping very well. You basically have to leave it up to the runtime, and you just have to wait to see if a program blows up to know if there's a problem or not, which isn't very good for landing airplanes. You don't want the code that lands the airplane to blow up in the middle of landing the airplane. You need to know ahead of time. You need to try to find as many errors as you can ahead of time, especially not simple errors like undeclared variable. That should never slip into a runtime error. It does in dynamically scoped languages. That's why they just really fell out of favor. There's just too many problems with dynamically scoped languages. Okay, then we go back over here. After we bind all the variables, then we just evaluate the function in the new environment. See, now I'm going to evaluate the body of the, if I go over here to the picture, after I bound this variable to that value, I'm going to evaluate the body of the function using the new environment. Whatever that new environment is chained to, okay, if that new environment is chained to this begin, then X is that. If this new environment is chained to the global environment, then X is that one. Okay. So let's go ahead and let's run. We've run the program with lexical scope. Now let's run it with dynamic scope. So to run it with dynamic scope, I go back up here to, where was it? Where I create the environment. Okay. The line where I create the environment, I create the new environment, the activation record chained to the local environment, the current environment. So instead of chaining the activation record to the global environment, I'm going to change it to the local environment. In our picture, that means that I'm evaluating apply in the environment of this begin. So then this apply sees that X. On the other hand, this apply will be evaluated in the environment of the global expression, of the global environment, because there is no begin block. On the other hand, this apply will be evaluated in the environment of this begin, because that's the current environment. So when this environment is created, it'll be chained to that one, which is chained to the global one, but then this function will see that X. Okay, so let's watch that happen. So I need to recompile. Oh, now I can't do that over here, because over here I was running, well, I have to rebuild. I'll do it by rebuilding the interpreter. Okay. The interpreter is being run by this, where is it? It's in this jar file. See, the interpreter right now is in that jar file. So what I want to do is rebuild it. So I want to rebuild that jar file with the recompiling the interpreter the way we just changed it. So build all the classes. Okay. Build the jar file. Okay. Now I can clean it, delete all the class files. I don't need them because they're now in the jar file. Okay. So now this jar file, this is the jar file with dynamic scope now. So now I can go back over to the shell. Okay. And if I run that program again, I'll be running it now in dynamic scope. So let's see. Oh, actually, let me clear the screen. Okay, and run it again. Okay, so now, we said what the output should be. We'll see. We know what if we're using dynamic scope, we know that like R will be 15 here, but R will be 6 here. Okay, actually, so just look for R right away. 15. Oh, I said, yeah, 15. See, there, R is 15. See, that's that R there. Okay, then the next R, the next block, 2,000. Well, why is it 2,000? Did I do something wrong? I thought it was 1,500. 1,005. Oh, let's trace through it. I bet, did that calculate something wrong here? Oh, I changed this to, oh, remember, that's what yeah, I added this thing, remember? So before, when I did this, there was no X here. Yeah. So now this is going to be, if I was using static scope, this would give me 1001. Okay, because it would take what the parameter would be 1000, it would add 1000 to 1. And if I use dynamic scope, the parameter is 1000. And then I'm adding 1000 to 1000. See, I'm adding this X is this 1000, but then when I get in here, this X is that 1000 again. So I'm adding 1000 to 1000, I'm getting 2000. Okay, right? So I don't know which way, it's probably comment out that's the way we had it before. Okay, so let me run it again. That's the way we had it before. Okay, so the R would be, see, there's R15, and we'll see, where's the next R? Oh, I'm losing it now. No, I'm sorry. We had it like this, and I had this as a 5. That was what it was before. That's what gave us 1005. Okay, yeah, we had, this creates the value for that X, and we had this one as a 5. See, we have F of 5 here. So that what gave us R as 1005. Okay, so that's what we had. So, okay, so there's R 1005. So there's R under dynamic scope. Okay, now if you notice the activation record, okay, let's trace through it. The code creates a global environment and puts X in it. Okay, then it puts F in the global environment. Okay, this line puts F in the global environment. Okay, then we begin a begin statement. Okay, so now we got the global environment with an begin statement hanging off of it, a local environment. In the local environment, we put X is 10. Okay, now we call a function, and here's where the things get interesting. See, now here's the function call on line 6. The function activation record is hanging off the begin block, which is hanging off the global environment. Before, the function activation record was tied directly to the global environment. So here's where that line of code changed things. This is where we changed the activation record to the begin environment instead of changing the activation record to the global environment. The effect that has in our code is that when we look up that X and we look it up in the environment, well, it's not local. See, it's not a local X. So we follow the chain and we find X there. See, we find that X. Well, that X was actually this guy here because that's the begin environment. So up here, this X found that declaration. We say that this X use found that X declaration. Okay, and that's what shows up here. That's the key thing. And in the 50s, when they were inventing this, they didn't even really think about, they didn't think hard enough about what they were doing. If they had thought really hard, they would have not have done it this way. They would have done the other one, static scoping. But this just seemed like the easy thing to do at the beginning, and they didn't realize the ramifications that they were doing this thing called dynamic scoping, which, yeah, and it took them a while to figure out what was going on. And by the time they figured out what was going wrong, dynamic scoping was kind of entrenched in the Lisp world. And people, and like I said, there are people who thought it was a fine idea. They liked it. And it took years for them to convince everyone to just drop dynamic scope. And Lisp now uses, well, actually, Lisp now uses both. You get to choose which scope you want when you run a Lisp program. Somehow you choose whether you use dynamic or static scope. Now the modern Lisp programming, like the classic Lisp programming language, lets you choose. All the dialects of Lisp that are in use right now, like Scheme, Racket, Closure, they all use static scope. None of them kept the dynamic scope part. But the official Lisp language itself still does both. I think it defaults now to static scope. It used to default to dynamic scope, but you could change it to static scope. I think now it might default to static scope, but if you want for backwards compatibility, you can still get the dynamic scope. Okay. All right. So there's the dynamic scope. The This activation record is now chained to that begin block, which is chained to the global environment. But that means when you evaluate the body of F, this X is that one, which is weird. Yeah. Okay. Then, if you go through, follow the code some more. After that, here the begin block goes away. Okay. And now the global environment is by itself. And then I call this function here. Now this function's like it was before because there is no, oh no, oh, I'm sorry. This is putting the result R in that local environment. So this one is putting R in that local environment. So after the function returned, then the return value is put into the local environment. So there's putting R in the local environment. Okay, so that ends line 6. Okay, okay. Then the next thing here, this begins line 9. Line 9 is just a function call, but there is no local environment. So now this function call gets tied to the global environment because, see, at this point in the code, there is no local environment. So the current environment is the global environment. So this F works the way it really should. This F has this X finding that X. Okay. Now, I could screw this program up. For example, suppose I do that. Now you get something really weird. That function call is okay, but that function call crashes. This function call is okay because it finds that local X in the local environment. This function call crashes because there is no X because I got rid of the global one. So watch, I'll run the program again, but now if I comment out that global X, this one will be okay, but this one will now crash because there is no global X. Okay, so save that code and then reinterpret it. Okay, undefined variable X. See, we crashed. Undefined variable X. If we trace through, that will be in this function call from line 9. It'll be line 9's function call. This function call will have been fine. All this evaluation up here would be here's the function call that succeeded. The activation record tied to begin block, that's the function call that succeeded here on line 6. Then after that, after the function call to line 6, the result was put in the local environment. This is putting the result in the local environment. Now we go to line 9. We go to line 9. We do an activation record. We create the activation record. Y is tied to the global environment. Then you evaluate this plus XY. Y comes from there. Oh, there's no X. And we get this error. So we're getting that error from that reference to X when it's called from here. But that reference to X is fine when it's called from here because it's that X. Okay, so notice with dynamic scope, you have more insanity that a function call in one part of the program can fail while the same function call in another part of the program can succeed. Okay, more reason why dynamic scope's a really bad idea. Okay, all right, so if I go back here, I can put back this one here. Okay, now there's a global X for all the function calls to use. Okay, and if we continue tracing through this program, line 9 was this second function activation record. Let's see. There's the first function activation record. So find the second one. Okay, this is the one. See, it's tied to the global environment. So that one, in this one, F is the global X. Okay, then now we go to line 11, which creates, oh, no, I'm sorry. R1 gets put into the global environment. That's this next block here. This is R1 being put into the global environment. So that finishes line 9. Okay, then now we're starting, well, now we create this begin block, which puts an X into the local environment. So that would be this. Okay, we create a begin, see, it's a begin block. We create this begin block and we put X in it and it's chained to the global environment. So there's that begin block. Okay, now we call this function F. Okay, the function activation record, we're using dynamic scope. So the function activation record now is tied to the begin block. So we have function activation record tied to begin block, tied to global environment. Okay, seems natural. Yeah, it took a while for these people to figure out that this was the wrong way to do it. It does somehow feel natural to say, well, this guy is inside this guy, which is inside that guy. But when it took them a while to realize it's not the right thing to do it, because you're calling this function inside of this begin block, but you're not defining the function inside of that begin block. And that's the key. The definition of the function's up here. It's where the definition of the function is that's important, not where you're calling the function. And that's what escaped them. That it seemed like, oh, I'm calling the function here. It's inside the begin block, which is inside the global scope. So local inside global. And it seemed natural, but it's not. It's all wrong. But it took them a while. And there are subtle places in computer science where these kinds of issues still come up. Like, what is the right environment to, for example, evaluate a database query in? Some places in computer science, you do want to use local scopes, not lexical scopes. There's all kinds of places where you evaluate things. So, you could be evaluating a query in a database. And different languages have different needs. So this local versus global issue is not a trivial one. In programming languages, everyone's settled on static scoping, but not everywhere. There are places in computer science where local scoping is a good idea, but not in programming languages. Okay, there are places where it would say, well, he's my X, so everyone should use him. And there's places where that would make sense. There's X, use it. So even though this is that X there, that X should be there. The idea being, well, I just created this X, you should be using it. In some distributed computing environments, or maybe like in databases, there might be a compelling reason to say, always use the most recent version of something. use the most recent version. Okay, so yeah, that stuff it's subtle. So it's worth knowing how this came up in one instance. In this instance, local dynamic scoping is a bad idea, but doesn't mean that it's a bad idea everywhere it comes up. If you created something, you very well may want everyone to use it until it's destroyed. So here X is created, here X is destroyed. In the meantime, everyone should be using that X, including that function call, maybe, maybe not. It's not a clear thing. With programming language, it became pretty clear that no, you don't want this function call to be using that X, not when the function's defined up here, and it should be that X. So programming languages should use lexical scope, but not every situation in computer science should necessarily use lexical scope. Sometimes the most recent is the one to use. Yeah, the most recent binding would be the one to use, not necessarily the global binding. Okay. All right. So we go over here and we trace through. Okay. This one is this activation. Okay. Notice that now picking up X is 1000. See, now in the function picks up X equals 1000. See, here's the function activation record. Y is 5, X is 1000, because you don't see that X if you stop there. See, when you look up things in the environment, you always look up the first thing you see in the environment. So when you look up X, that's what we mean by saying that X hides that X, because you follow the chain and you look for the first X in the chain. So that X hides that one up there, because that one comes first in the chain. Okay. So, okay. Now, after this, now you put their R into that local environment. That's this one here. That puts R, the result, into the local environment. Okay. Then I call this guy. This is another one where there's where the current environment is the global environment. So here's the activation record with the activation record tied to the global environment. Because here I'm at the top level. I'm back to the global level. This is running at the chain. This is running in the global environment. Okay, there is no begin block at this point. Okay, so I call the function in the now the X is the global X. Okay, then that result gets put into this one is that result being put in the global environment, and this last one here, this is that call right here. This is that's this funny last line here. Okay, notice it doesn't create any variables, but it does create an activation record. So this one calls F with parameter 4. So there's Y with parameter 4. So there's Y with parameter 4, and F is chained to the global environment because we're calling F in the global environment. Okay. All right. So there's a trace of dynamic scoping. Okay. So there's a trace of this program using dynamic scoping, and it's not pretty. It's not a good idea. Dynamic scoping, as I keep saying, dynamic scoping really fell out of favor. You won't find very many programmers who think dynamic scope's a good idea. So if you go back and look at those Wikipedia pages, I bet you can find one where somebody writes about how dynamic scoping can be made, how you can do useful things with dynamic scoping. Okay. Like here. Well, I don't think dynamic scoping is useful for anything, but here's somebody trying to make an argument where, oh, look, you can do clever things with dynamic scoping. You'll still find people arguing that dynamic scoping is not all bad. Or even that dynamic scoping is a good tool to have in your toolbox. That's another one of the funny, it's a nice tool to have when you need it. And the answer pretty much modern days is no way. It's just not a good idea. But you will find plenty of people kind of defending dynamic scope. Okay. Okay. And if you read through these, I'm sure you'll find a few other people. Oh, Lua use dynamic scoping? Lua is a pretty popular language. It's used a lot in the gaming industry. No, it's not found in many other languages. Oh, wait a minute. The scoping that most programming languages use is called lexical scoping. It's found in Lua and so does Lua use both? Well, it said here that lexical scoping is the dominant choice for a reason. I don't know, maybe Lua is one of the languages that lets you choose which one to use. That would, yeah, that's not, I mean, I don't think it's such a great idea. Dynamic scoping is a mess. If you write code using dynamic scoping, you're basically telling the people who read your code, good luck with this. Yeah, it makes code impenetrable. So even though you might feel like you can do clever things with it, it makes people, anyone who has to read your code, debug your code, maintain your code, you're not helping them at all. So I mean I guess I forgot I guess Lua maybe has both. Like I say, it defaults to lexical scoping, but see, does it say you turn it on somehow? I guess it's a keyword. You declare a variable as dynamic. You declare variables as dynamic. Okay, at least then people get a clue that you're doing something funny. You're not making this. You have to say that the variable is dynamic. So in our code, that would be like, uh, I suppose in our code, that would mean that you could do something like up here. You could say either you could say do use this thing lexically or dynamically. If you didn't say anything, this would be a lexical variable, so it would be that one. But you could, I guess if it was Lua, you could say this variable is dynamic. Yeah. Oh, and then you would do like dynamic scope. You would just use the most recent version of X. Okay. That would mean that at runtime, their evaluator has to maintain two chains, a global one, one that's, yeah, it would have to maintain two chains, or do some kind of weird tricks because it would have to at runtime figure out whether it needed to look thing up dynamically using one chain or statically using a different chain. Okay, so now notice that one reason we're learning this is because it's there in programming languages. Like Lua is actually a pretty popular language. At one time, it was a pretty popular language in AI, but then the AI people moved away from it to Python, and it's still a popular language in the gaming community. It's used as a scripting language by a lot of game engines. Yeah, so Lua's up. People think of it as a very elegant, nice language. And it's got this quirk that it allows a form of dynamic scoping. Well, you need to understand, it helps to understand dynamic scoping to see what they're talking about. I'm not sure why they do it. Probably the person who invented Lua is just one of those people who thinks that dynamic scoping is cute and that you could do interesting things with it. You can do some kind of clever things with dynamic scoping, but the general consensus is they're so convoluted and so easily misused and so prone to being buggy that it's just not a good idea. It's just not worth the effort. Even if it can do something clever, you know, it's not worth the price. The price and the pain you get from debugging the code is just not worth the cleverness. Okay, but yeah, it's worth in a programming languages course like this, we should cover all these different concepts because even the dead ones like dynamic scope don't ever really go away. They just somehow manage to stick around even in, somebody will create a language like Lua, which is popular, but they'll stick some old-fashioned idea in it for whatever reason. I'd have to read up on Lua to see why they wanted dynamic scoping in there. Because Lua is not an old language. It's a relatively new language. So when Lua was invented, definitely the world was frowning on dynamic scoping. By the time that Lua got invented, I think the whole world pretty much frowned on dynamic scope. So I'm not sure why they put it in there. The other languages that have dynamic scoping tend to be really old languages that have been around a long time. So that's Lisp, and Perl and a couple others. They tend to have it because they're from the 70s or 80s. Lua, oh, when was Lua invented? Well, I don't think it's an old language. Okay, in the 90s. By the 90s, yeah, dynamic scoping was really out of favor. It fell out of favor in the 80s. Okay. Well, it doesn't mention dynamic scope in this page. It's dynamically typed. That's a different issue entirely. We'll talk later about dynamic typing, but dynamically typing is completely different than dynamically scoping. Dynamic typing is real common these days. Dynamic scoping isn't. Okay. All right. So that's the last thing we wanted to do with language 7 was this distinction between lexical and dynamic scoping. So now we're ready to turn to language 8, which is real functional programming. We'll see that language 8 really takes us up to modern languages. It's Scheme and Haskell. It's got features of it's got a feature. It's got one feature that distinguishes modern programming languages. These things called closures. So it's got one feature that makes it an ultra modern language, and it's lacking a lot of other things. It doesn't even have an arrays or data types, or doesn't do reals or strings. But language 8 will let us add this one ultra modern feature, closures, which only recently was added to Java and only recently added to C++. When I say recently, in the last 10 years, it's somewhere like the last 10 years. Java's been around for almost 30 years, but it's only in the last like 10 years or so that it got at closures. Same with C++. Closure, yeah, C++ got them in 2011. C++ got closures exactly 10 years ago, but C++ has been around since the 70s. And it didn't get closures for 30 or 40 years. So we're going to take language 7 and give it what's called closures, which is a very important idea to understand in modern programming. Okay, so if you have so we'll quit there. If you have questions about the homework assignment, send me email or come to office hours. And so we'll meet on Wednesday. I'll put language 8 up there on the website after class. So I'll put it up there, and then we'll start talking about it on Wednesday. Okay? Any questions?
I have one,
Yeah.
one quick one. Could you give one good example for repeat, like the two expressions, the body and the bool, so I can try and
Say again, to do an example of what?
repeat
I mean,
for
the repeat loop?
yes. Like in the homework, they're all 4s, and I'll
Wait a minute. Did I forget to put a repeat example in the homework?
I didn't see one personally.
Oh, somebody should have pointed that out.
I might have just missed it, but
it's very possible I missed it, because I added the repeat to this homework assignment. It wasn't in there last year.
Okay.
So yeah, I may have forgot to put it in the test cases, because I added it. So we'll see. Where's the test cases? This one,
Yep.
right?
Mm-hmm.
You're right. There are no test cases of repeat, are there? So I'll add some to this, but you can make up your own. Yeah, make up a repeat loop. Yeah, I'm sorry. I added the repeat loop, and I forgot to add it to the test cases. Did I have it in one of the other test files?
I looked in the first part too, the language 6 examples, and I didn't see one there.
No, it wouldn't be in there because it's only part of language 6A. It's not part of language 6.
Okay.
Yeah, it wasn't in the original language 6. It's in language 6A. Oh, well, yeah, that's a mistake. Yeah, there should be. Yeah, you'll have to, if you want, you can wait. I'll put some examples. I'll put a couple repeat loops in there. But if you want, you can add your own.
Okay, I'll
just repeat a print statement or something like that. Yeah.
All right.
Yeah, but that's a mistake. There should have been repeat loop tests in the test cases. Okay. Yeah, when you guys see things, yeah, I've got a 5-course teaching load. I'm going nuts trying to keep up with all these courses. I'm really having, it's a real struggle to keep up. So when I got that homework assignment up, I haven't looked at it now in 2 weeks because I've had just too many other things to deal with. So if you find mistakes or if you think there's something wrong, please tell me, because it's hard for me to look at this stuff real carefully over and over again. I just don't have time to. Okay, so yeah, I'll add a few repeats in there. And
Okay.
then but definitely you want to test your own code. You could even test it in the REPL loop. You could
Right,
write a
that's what I was gonna do.
yeah, you can just type a repeat in your REPL and make sure it works. And I'll try to add a repeat to the test cases, but you can test one in your REPL real easily. Okay.
So would it be like repeat an expression? So just print something, and then the second expression would be like
A Boolean.
uh yeah, like a Boolean, like until I equals or I
Uh-huh.
less than 10.
Yeah, uh-huh. So
Okay.
let's see, yeah, it's just like a while loop, but you just you switch them around. You switch around you do this is the Boolean and this is the thing that you do. So for the repeat loop, it's the other way around. Well, repeats, yeah, it's the other way around. This is
Okay.
what you do and this is what you check. Yeah. So you print, then check a Boolean, like
Got it.
I is less than 10. So here you print I, increment I, then test it. So it's just take any while loop and flip over the order of things. And then it becomes a
Uh,
repeat loop. Just take any while loop and just kind of flip it, put the Boolean at the end instead of at the beginning, and it becomes a repeat loop.
okay.
Yeah, and you can do some clever things with repeat loops. That's why Java and C all have them. That people tend to use while loop a lot more often, but all of the languages have a repeat loop because every once in a while you can write code a little bit more elegantly using a repeat loop than on a while loop. Okay.
Cool.
And I'll try to, yeah, tonight I'll add a couple repeat loops to the official test cases, and I'll make them part of the output of the test case. Okay. But yeah, and meantime you can test it in the REPL. Okay. Any
All
other
right.
question? Okay. So we'll meet again on Wednesday, and we'll start language 8 then. So see you Wednesday. Bye bye.